Hello everyone, my name is Kintek Lee, and today I'm going to present our work on aggressive perception-aware navigation using deep optical fluid dynamics and PixelMPC. In this work, we introduce deep optical fluid dynamics, which is a combination of optical flow and robot dynamics. With this new concept of dynamics, the suggested pixel model predictive control algorithm controls the robot to accomplish a visual servoing task as well as a high-speed racing task while maintaining visibility of important features. This presentation is organized as follows. We first start with the motivation of this paper. Then we briefly review some preliminaries used in our work. The deep optical flow dynamics and the PixelMPC algorithm will be introduced, and we will show vision-based drone racing experiments and state estimation experiments with robust vision information. The motivation of this paper comes from the drone racing competition we participated last year. The goal was designing and developing AI to pilot drones through professional drone racing courses. The goal of this work is to do high-speed drone racing with improved visibility. When we fly a drone in high speed, it pitches down and becomes myopic and loses its visibility to important features far ahead. This reduces the performance of vision-aided state estimation, where the robot states are estimated through localization and mapping. The visual information is critical for this kind of localization problem, and it's not trivial for a drone to get a lot of visual information when flying in a high speed. Most of the previous work on vision-based drone flying method follow these steps. First, they find a target in the image obtained from the camera and calculate the distance between the center of the image and the target. Then a simple PID or feedback controller can be used to rotate the drone until the target is in the middle of the image. And then they fly straight towards it. This approach is too slow because we have to wait until the camera sees the object in the center of its view. Another problem of this approach is that it is not predictive. We introduced the concept of controlling the pixel dynamics. Why do we call it dynamics? Because controlling the robot implicitly moves the pixels. In these four examples, what should we do if we want the target door to be at the center of the image? In the upper left case, we can move the camera 45 degrees down right. In the upper right case, we can move the camera 45 degrees down left. As a result, controlling the robot moves the pixels and accomplish a task of putting a target in the middle of the camera's view. From this, we can find that there exists implicit dynamics between the control of the robot and the pixel movement. Optical flow estimates the velocity of objects and features in a visual scene from a sequence of ordered images. Usually the optical flow prediction methods, for example, the FlowNet uses a unit-like architecture which takes a sequence of images as an input and predicts the whole image-sized optical flow. In our work, first we depend on a detector which detects target features in real time. Our work depends on a simple three-layer feed-forward neural network by taking only the single pixel position, which is the center of the target, robot states, and control. The simple network learns the implicit dynamics between the robot dynamics and the dynamics of the target pixel. Since we don't rely on a large network and we only predict an optical flow of a single pixel, it is computation efficient. Also, our approach is data efficient because with a single image data, we can generate thousands of training sets. This plot shows the runtime of our approach and the fastest state-of-the-art optical flow prediction method. Our method is suitable in an MPC framework where it requires sequential computation along multiple time steps. It also fits perfectly with any kind of sampling-based control frameworks because our network is small and light enough to be parallelizable, whereas the other approach runs out of memory when we try to sample hundreds of predictions in parallel. We first collect a training data by running MPC and storing the image pair optimal control action and the corresponding optical flow, which will be used as a target. As we see in the training phase, we train the model for each pixel in each image, so this is why our method is data efficient. At the testing time, the trained deep optical fluid dynamics predict the velocity of the target pixel given only the robot state's target pixel and the control, which can be generated in a typical nonlinear black box dynamics model. This video shows the performance of the deep optical fluid dynamics, and the DOF predictions are applied to all pixels as a comparison. The MPC optimal control problem is formulated like this. Given a cost function, the goal is to calculate an optimal control policy subject to system dynamics. We introduced the PixelMPC algorithm where the task is controlling the robot to achieve two goals simultaneously. The first goal is to move the target pixel to the center of its image, and the second goal is performing a high-speed racing task. The PixelMPC propagates both robot dynamics and the pixel dynamics at the same time. As a result, the optimal control policy controls the robot to achieve both tasks. In this slide, the first graph shows the increased visibility when we use the PixelMPC compared to a nominal MPC controller only having a high-speed racing task. In the second graph, as expected, we achieve better visibility, but at the cost of a small amount of speed. Here are two videos to show a comparison. The first video is running on nominal MPPI, and we see a lot of shaky movements and losing the target for about 20% of the lap time. The next video shows our PixelMPC algorithm, and we can see it doesn't lose its target in the scene and having less shaky movements as a byproduct. This video shows the nominal MPPI running without having any visual servering task. The pink blob around the vehicle represents the variance of the particle filter. We can see the estimation uncertainty grows a lot when it loses the gate in its view for a long time. This video shows the PixelMPC running with the visual servering task as well as the high-speed racing task. We can see the estimation uncertainty remains smaller than the previous case because as soon as the camera sees the target, it remains in the image. With this less variant state estimation, PixelMPC shows outperformance on success rate of the state estimation-based racing task, where the failure cases happened when the state estimation was not accurate and resulted in a crash to gates, walls, or other objects. The green trajectory shown in the image at the top represent 2 seconds of future pixel trajectory. Thank you for watching this presentation, and if you have any questions, please feel free to contact me.